In this lesson, what we are going to do is introduce the notion of a Taylor series. The context here is suppose that you have a function f of x, which you know to be infinitely differentiable on the open interval centered at a of radius r. If that function has a power series representation, then the coefficients must take a particular form. Notably, c sub n for each index n can be found by taking the nth derivative of the function, evaluating it at a, and then dividing that by n factorial. So here, the superscript n refers to the nth derivative of f. These are called Taylor coefficients. When you put them together and write out the power series for your function with these coefficients, that's what we call a Taylor series. So the first thing that we're going to do in this video is derive this form. It's a computation that I would encourage you to revisit on your own later. So see if you can reproduce the first result that we have in this video. Then I would like to just mention kind of an alternative version of the ratio test to talk about the radius of convergence, and then we'll wrap up this lesson with a fairly challenging example. In the next few videos, we will compute Taylor series for some famous functions, and you might actually find those examples a bit easier than the example that we do in this video. Let's work through the derivation of those Taylor coefficients that we just met. I'm going to work through this for you now, but I really do encourage you to rederive these later on your own, because I think once you've gone through the mechanics of the computations a few times, it solidifies why Taylor coefficients have to have the form that they have. Okay, so here's what we're going to do is imagine that we have a function f of x, which is infinitely differentiable on some nice open interval around the center point A, and it has a power series representation that initially looks like this. The goal with Taylor series is to say, hey, for this infinitely differentiable function, we can do better than just c sub 0, c1, c2. We can give a much more descriptive form for those constants. So what we're going to do now is find a way to essentially solve for those constants so that we can say Taylor coefficients aren't just c0, c1, c2. They have a certain form. Okay, what I'm going to do is take f of x and its series expansion. I'm going to write out the first few terms. Then I'm going to plug in the center a so that we see what f of a is. Set that aside. We'll differentiate to get f prime of x. For practice, I'm going to differentiate both the series expression as well as the expansion, and then we'll plug in a, set that aside. Take the second derivative, series, expansion, plug in a. So we're going to keep differentiating f of x. Every time we differentiate, we will then evaluate our new derivative at the center point A. Every time we do, we're going to notice that the same thing happens. Okay, so let's do it. F of x, I'm just going to rewrite everything, has a power series expansion, or a power series representation that looks like the sum from n equals 0 to infinity, c sub n x minus a to the n. And then as we know, when we expand that, that's going to be our first constant plus c1 x minus a plus c2 x minus a squared, etc. What is f of a? So maybe I will do that just below. Well, this happens for every power series. It converges at its center, and what it converges to is this leading constant. So all of these terms are 0 when I plug a in for the independent variable x, leaving us with just the first constant. So we've already got our first constant. The goal is to find a descriptive form for these constants, and here's the descriptive form for c sub 0. It's just f of a. Okay, now let's take the derivative. So what is f prime of x? I'm going to do this kind of two different ways. The first way is just to work with the sigma notation. I think it's good practice to see that. To differentiate this with respect to x, I'm going to use the power rule. The n comes down, that becomes n minus 1. But when we differentiate, we lose any leading constants. So if there's no x dependence here, that turns into 0. So we're going to lose the n equals 0 term, which means our new lower index starts at n equals 1 and goes off to infinity. C sub n times n, where that exponent came in front, times x minus a to the n minus 1. To expand this, you have two options. You can either start plugging n values into this, or maybe it's a little faster to just differentiate this. We lost that first term. Then we have c1 plus c2 times 2x minus a to the 1. And then I think I'll just dot, dot, dot. What is f prime of a? That's the procedure that we follow to get these Taylor coefficients is differentiate, plug in the center, differentiate, plug in the center. That's going to lead us to the general form. Well, this is also a power series, and it has the same property as the previous one. When we plug in the center, everything that has the x minus a term gets wiped out to 0. So the only term that we see is the C1. It's C1 plus 0. So f prime of a is C1. So there's our descriptive form to replace this next constant, C sub 1. Don't spot a pattern yet, because we're going to see something a little different happen when we take the second derivative. Okay, so let's do f prime of x. And again, I'm going to try to do this kind of with the sigma notation and with the expansion, so it's really clear what's happening. What is f double prime? Again, when we differentiate, we're going to lose that leading C1 term. Our first n value will actually be n equals 2. So we bump up from n equals 1 to n equals 2. Then with the power rule, the n minus 1 will come down, and our new exponent will be n minus 2. So we will see Cn times n minus 1, x minus a to the n minus 2. So this is like the power series representation for f double prime. If I come here and start differentiating, the first term is 0, so derivative of just the constant C1, that goes away. We then have 2C2. For the next term, in order to see it come out of the expansion, you'd need to add another term over on the right-hand side, but I'm just going to work off the sigma notation. We are looking at the n equals 3 term, so that's going to be C3 times 2 times x minus a. So I'm going to write 3 times 2 times C3 x minus a. And then I will write dot, 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 knowing that every other term in the power series expansion is going to have this x minus a factor appear. That means that when I plug x equals a into the second derivative of f, this gets wiped out, as does every following term. So f double prime at a is just this leading 2C2. Okay, so it wasn't just C2, careful, it's a little different. I think if we do the third derivative, we will have enough to then summarize with the nth derivative. What I would like for you to do is pause and write out the third derivative of f of x. In sigma notation, expand as many terms as you would like, and then plug in x equals a to the third derivative. I will come back and do all that work down here, at which point I think I'm going to need to erase all of these. We'll keep in mind what the result of evaluating f and its first 3 derivatives were at x equals a. We'll summarize the general formula in terms of the nth derivative, and that way we will arrive at the Taylor coefficients. Okay, here's what I hope you got for the third derivative of f. If we differentiate the line above, we'll have f triple prime. The lower index will bump up once again, so that we're indexing from n equals 3 to infinity. Power rule again. So we'll have c sub n times n minus 1 times n minus 2, and that kind of decreasing term behavior is what's going to be key to writing down the general form, times x minus a to the n minus 3. And if I write out the first couple terms, then when I plug in n equals 3, we have 3 times 2 times 1. Let me write all of that. 3 times 2 times 1 times C3 times x minus a to the 0, so it's just a constant. And then the next term would be when n equals 4, 4 times 3 times 2, C4 x minus a. And I don't really care about that term or anything that follows, because what we're about to do is plug in a for x, wiping out everything here, so that we can conclude that f triple prime at a is this expression. Now, 3 times 2 times 1, it's really 3 factorial. So let me write that this time. 3 factorial C3. Let's revisit the previous computations and see if that looks like this is the right type of notation to use for the other derivatives. I wrote 2 here, but actually, for this second derivative computation just on the line above, this first term comes from plugging in n equals 2. And when I do that, I get the C2. I get 2 times 1, really. So this, if I wrote out every single term there, even the 1, it would be 2 times 1 times C2. So really, this was 2 factorial C2. Similarly, this was just plain old 1. We could think of this as 1 factorial times C1. Okay, so this factorial is going to be key to describing the nth coefficient in terms of the nth derivative of f. So given that we're out of boardroom now, let me erase all of this, and I'm going to write down kind of an analogous expression for the nth derivative of f evaluated at a. Let's now write down an expression for any derivative of f. I'm going to call this the kth derivative of f to avoid overusing the letter n. So I'm going to say the kth derivative of f, the function f of x, has a power series representation where we're going to index from the lower index for n will be the order of the derivative. So if you compare that to the Taylor series expansions that we wrote down for f prime, f double prime, f triple prime, you should agree with this lower index off to infinity, c sub n, and then we kept bringing powers down so that we get c sub n times kind of a product that starts to appear. And what that product will look like is n times n minus 1 times n minus 2 times n minus 3, all the way until you get to the term n minus k plus 1. So these represent exponents that came down through successive iterations of the power rule. Now times x minus the center a to the n minus k. Okay, this expression might look a little strange, but if you map it into what we did with f prime, f double prime, f triple prime, I hope you agree with this. Let's now see what the first term, maybe first 2 terms look like if I actually write out this expansion. When I plug in the lower index of k, we get c sub k times k minus 1, all the way through k minus k plus 1, so all the way through 1, x minus a to the 0. Okay, so that's really just a constant. Plus the next term, so that would be c sub k plus 1 times k plus 1 k all the way down to 2, x minus 1 to the first power, and then everything after that similarly has an x minus a term. Okay, so this is just 1. All right, what that means is that if I now plug in the center, x equals a, we can say the kth derivative of f evaluated at a, well, all of this goes away, that's all 0. This is 1, we get c sub k times k factorial. Okay. Now all we have to do is solve for the coefficients. That was the goal of this exercise, was to be able to replace those unspecified coefficients in the power series for this function with something a little more specific. So now we're saying that the coefficient c sub k is the kth derivative of f evaluated at the center divided by k factorial. If you compare this to what I wrote down on the first slide, I switched from n to k, but it's the same idea that this just represents an index. So this could be C0, C1, C2, C3, C4. So k just runs through the indices in our series. The reason why I made the switch from n to k, in case you're curious, is because I was already using n to index through my series, and I didn't want to switch this up. I thought it was better to switch the derivative order up. But here is the formula for any coefficient in this kind of Taylor series expansion for a function which you know to be infinitely differentiable on this nice open interval. Okay, so this, again, is something that you should be able to rederive. If you work through, maybe just the first couple derivatives, you can get to this again. One of the biggest mistakes I see students make, and I also make this too, so I might really be talking about myself here, is I will often take the derivatives of f. If I start trying to crank out these coefficients, I'll start taking derivatives, plugging in a, and I totally forget about the denominator. So whenever you're working through Taylor coefficients, as we will in a minute, don't forget the k factorial in the denominator. Just take it from me. You will at some point. I still do always forget this denominator. So make sure that you don't get so content with taking the derivatives of f that you forget about the k factorial. Okay, I am going to step away from this derivation now. Then we are going to talk about the radius of convergence, and also I will conclude with a challenging example. Let's talk about how to find the radius of convergence. Suppose we have an infinitely differentiable function f, which has this Taylor series representation. Notice this is just a regular power series where we've given the coefficients that special form that we just derived. What I'm going to do now is just mention how to find the radius of convergence. And what I'm going to say is actually not just true for Taylor series, it's something that you might have already arrived at for power series in general. So how do we find the radius? Well, typically we would try the ratio test, and that's still valid here. So let me write that as option 1. To find the radius, the radius of convergence, you can try the regular ratio test as we've always done it. Here is another option. It's kind of like a reduced version of the ratio test. And again, it's something that you might have already realized just by working with regular power series. And what happens is if you notice that the coefficients tend to a certain limit, you can extract information about the radius from that. So let me write this down. Suppose this limit exists. So suppose if I set up the limit as n goes to infinity of just the ratio coefficients, so Cn plus 1 to Cn, right here, it doesn't actually matter that I've given them this special form. Suppose that this limit exists. So let me say it's equal to some number m. Then the radius is 1 over m. I'm writing this here as if m was a finite positive number, but we can also extend this to the cases where the radius is 0 or infinite. So if m is 0, the radius is infinite. If m is infinity, so if this limit blows up to infinity, then the radius is actually 0, and that's usually a Taylor series, at least that we're not so interested in because we're looking at functions which are nicely differentiable on an interval, but I'll mention it here. Let me justify that this happens. So this is going to come out of the regular ratio test. So let me just show you why we have this inversion here. We're going to suppose that this limit does exist. So suppose that if I set up the ratio of consecutive coefficients like this and take the limit as that absolute value of the ratio goes to infinity, take the limit as n goes to infinity of this expression, that's what I'm trying to say. Suppose it exists and equals m. Let's see what we could get from the regular ratio test. Okay, so here's what we're going to do to set up the limit as n goes to infinity of the regular ratio test. And again, I actually can just work with the general power series. So how about Cn plus 1 times x minus a to the n plus 1 divided by Cn x minus a to the n. Well, we can immediately compute this limit with this hypothesis. The x minus a terms simplify greatly. And then I'm assuming that this goes to this number m. So overall, this limit will be m times the absolute value of x minus a. For convergence with the ratio test, we want this less than 1. That gives us the radius of convergence. So let's say we want this less than 1. Let me continue the computation over here. I could say that that means that x minus a is less than 1 over m. Right here I'm working with the case where we're assuming we have a nice positive number. If I unfold this inequality, we've got negative 1 over m less than x minus a. less than 1 over m, add a to everything, and you get that x is situated between a minus 1 over m and a plus 1 over m. In other words, this is a radius of 1 over m. So x is within distance 1 over m of a. So that's where that inversion of this ratio comes from. Were it the case that m were 0, then we would actually not need to do any of this, because when we did our ratio test, we'd say, hey, 0 is always less than 1, so this converges for all x. So were this 0, we would stop here. Similarly, if this grew to infinity, then we would be looking at the situation where if x equals a, we can actually wipe that out to 0. We could say that we get convergence at the center. If x is anything other than a, it would blow up to infinity, so we would be looking at a series that only converged at the center. Okay, so that's just a quick look at radius of convergence. There's nothing really new here. It all kind of comes back to the ratio test. So if you're comfortable with the ratio test that you've been using, you can stick with that. If you like this idea of just looking at the ratio of consecutive coefficients like this and finding out if this limit exists, then you could try this approach as well. Now that we've said what Taylor coefficients are, let's find them for a given function. So we will find the Taylor coefficients for f of x equals 1 over the square root of x centered at x equals 16. It will be helpful to think of this as x to the negative 1/2 power. Even so, this is going to be a fairly intense computation for Taylor coefficients. I think it's harder than future Taylor coefficient computations that we do. So this is kind of a big example. We will find those Taylor coefficients. We will find the radius of convergence. I will use this alternative form of the ratio test that we just talked about, but you can also use the regular ratio test for that. And then we will wrap up by applying our Taylor series computation in order to get some information out of it. So we will use our Taylor series to estimate the value of 1 over the square root of 17. Let's find the Taylor coefficients for f of x equals 1 over the square root of x centered at x equals 16. This is going to be a bigger computation than future Taylor coefficient computations we're going to do. So in some ways, this is like the hardest example that we're going to see. Be organized with your work. So let me try to be as organized as I can on this board. What I'm going to do is write down f of x, and then I'm going to start writing down the derivatives. We are going to just differentiate. Then we will evaluate those derivatives at the center x equals 16. What we will need to do at that point is try to come up with a way to write down the nth derivative of f. That's ultimately what we need in order to say what the nth coefficient looks like. That's an exercise in pattern recognition. So as you take these derivatives, start to try to see the patterns as they happen, and I'll highlight them when we start to notice them. So our 0th order derivative, it's really just the function, f of x, which I think it's better to write as x to the negative 1 over 2. Differentiate with the power rule. We get f prime of x is negative 1/2 x to the negative 3/2. Okay, let's differentiate again. F double prime is going to be, let me put the 3/2 in front. We'll have negative negative, so that's positive 3/2 times 1/2 x to the negative 5/2. You can start to see some patterns emerge. Let's take another derivative at least. The third derivative, I'm trying to write 3 primes here and I think I'm making it worse and worse. Looks like 6 primes at this point. Okay, the third derivative of f is the 5/2 is going to drop down and we're going to pick up a negative again. So you start to see a pattern with the signs here. We now have negative 5 over 2 times 3 over 2 times 1 over 2 x to the negative 7/2. I would recommend not multiplying these together. I would not write 15 over 8 and 3 over 4. Because sometimes when you're trying to spot a pattern, it's easier to spot the pattern in the factors than in the product. So I think it's easier to see, hey, 1, 3, 5, that feels like a pattern. That might be easier to work with than 1, 3, 15. So that's my advice, is not to combine, multiply things together. If you leave it in factored form, you might be able to describe the pattern more easily. The next is go until you see the pattern. So can you immediately know what the fourth derivative would look like? And then check yourself. Hopefully at this point, it's clear what's happening. Let me go ahead and write the fourth derivative. The negative 7/2 is going to come down. We're going to flip back to positive. Then we'll have 7 times 5 times 3 times 1 divided by 2 times 2 times 2 times 2. So there, put it in one fraction, but it's the same ideas. We've got these four terms multiplied together, x to the negative 9/2. Okay, I think I know what's going on at this point. It's just a question of translating ideas into mathematical expressions. What we have in the numerator is a product of odd integers. So 1, 3, 5, 7. The next one would be 1, 3, 5, 7, 9, right? In the denominator, we see just twos. Twos multiplied together. How many are there? Matches the order of the derivative, so that's great. So we've got second derivative, 2 twos. Third derivative, 3 twos. Fourth derivative, 4 twos. That's good. Then we have x to the, and then notice that this numerator is also an odd number. It's the next odd number following the 7. So I think the hardest thing to do at this point is describe these odd numbers. Some people do this very quickly. If you don't see how to do it, you can try to write down like a map. We can start with first derivative went to numerator 1. So the first derivative, the highest odd number was 1. The second derivative, the highest odd number was 3. For the third derivative, the highest odd number was 5. I'm looking at this number here. For the fourth derivative, it was 7. Can you write down an expression that takes 1, 2, 3, 4 and converts them into 1, 3, 5, 7? It's actually a straight line, so you could write down a line. Or what I would do is say, I'm going up by 1. Here I'm going up by 2. So it's like slope 2. So there's a doubling action happening here. Once you realize you've got to double these numbers, then you just need to adjust it to get to 1, 3, 5, 7. Okay, so double would be 2, 4, 6, 8. I need to subtract 1. I want to conclude that the nth derivative of f takes a form that we can now describe. We have alternating signs. The even derivatives, 0, 2, 4, they were positive. The odd derivatives, 1, 3, had we written down the fifth derivative, that one as well, they were negative. That's going to look like a negative 1 to the n. Then we have a product of odd integers, where the highest one is twice the derivative minus 1. So from 8 to 7, 6 to 5, 4 to 3, 2 to 1. So that's going to be 2n minus 1. And then we multiply on down to 5, 3, 1. So how about 2n minus 3 down to 3 times 1? Okay, that's that numerator. The denominator is easier than the numerator. It's 2 raised to the order of the derivative. So that would be 2 to the n. And then we have x to the negative 3, 5, 7, 9. That's actually taking this doubling action and adding 1 to it. So that would be 2n plus 1 divided by 2. We now have the general form for the nth derivative of the function f of x. I think I said I was going to plug 16 into all of them, but there's no need to do that. Let's just plug 16 into this expression. So what we can say is, what is any derivative of f evaluated at the center, x equals 16, because that's where we need to do our coefficient computation, is at the center. This part's not going to change. So that's negative 1 times this product. Here, this expression might be easier to evaluate if we realize, I'm trying to switch markers to a different color, if we realize that x to something divided by 2 is like square root of x, that's x to the 1/2, to that numerator, like that. So I've just rewritten this fractional exponent as x to the 1/2 to the negative 2n plus 1. So that's square root of x to the negative 2n plus 1. Okay, so that's going to be the square root of x is 4. To the negative 2n plus 1. Like that. Okay. Let me make this look a little bit better. I forgot the n here. That's one thing that I should improve. Let's go down on another line. We'll have negative 1 to the n times this odd product. Four to this negative exponent is like 1 over 4 to the 2n plus 1. So we'll do 2 to the n times 4 to the 2n plus 1. And then I would like to write this one more time. It's not totally necessary, but 4 is 2 squared. So if I convert it to base 2, I can combine these two denominator expressions. So this is 2 squared to the 2n plus 1, which means that my final form for the nth derivative of f evaluated at 16 is going to look like negative 1 to the n times the odd product divided by this product here. I'm going to have 1 base 2, and then I'm going to say n plus 4n is 5n plus 2. So 2 to the n times 4 to the 2n plus 1 is the same thing as 2 to the 5n plus 2. This is where you've done all this work, and it's tempting to just stop here and say, okay, I'm done. I found the coefficients. But this is the nth derivative of f evaluated at 16. It's not the coefficient. All that remains to do is divide by n factorial. So we are basically there. Now we just say that the coefficient c sub n, which we will see in a series expression on the next slide, is this divided by n factorial. Just going to include the n factorial in this denominator. So how about the leading alternating sign times the odd product divided by this denominator times n factorial. Okay, now we have found the Taylor coefficients for f of x equals 1 over the square root of x centered at x equals 16. On the next slide, we are going to write down the Taylor series for this function. We've got most of it here. The coefficient is most of the expression, but we'll put it in the series notation, and we will find the radius of convergence. Now with the coefficients that we just found, we can write down this Taylor series expression for 1 over the square root of x centered at x equals 16. So you can see it's a power series, just with the coefficients given the specific form that we worked out. Let's find the radius of convergence. And what I'm going to do, because there's already a lot going on here, is just try that test that I mentioned where we look at the ratio of consecutive coefficients. So we can say, what is the limit as n goes to infinity of the n plus 1th term divided by the nth term? So the n plus 1th term, I'm going to omit the negative 1 to the n because that's not going to matter. If I do 2 times n plus 1 minus 1, I get 2n plus 2 minus 1, so 2n plus 1, and then it would be the next odd number all the way down. Okay, so that's the numerator for the n plus 1th term divided by the denominator. So that's going to be 2 to the 5n plus 5 plus 2. So 5n plus 7 times n plus 1 factorial. Okay, so this whole expression is what we can think of as Cn plus 1. So everywhere I had n, I replace it with n plus 1. Now let's multiply by the reciprocal to divide by Cn. So that's going to be 2 to the 5n plus 2 times n factorial divided by the original numerator. So that's 2n minus 1 all the way down to 3 times 1. Everything here is positive, so we can get rid of the absolute values on the next step. We also have a lot of cancellation that's going to happen. Notice this whole denominator will divide into this numerator, canceling out all but the first term. So that's nice to see. The n factorial will divide into the n plus 1 factorial in the way that we've seen a lot. Let me write n factorial cancels out the factorial part of that, if you know what I'm trying to say. So n plus 1 factorial is like n plus 1 times n factorial. So we canceled out that n factorial. And then these 2's will also simplify, leaving us with the limit as n goes to infinity of, this will divide into that, leaving us with just 2n plus 1 in the numerator. And then here the 5n's cancel. 7 minus 2 is 5, so we're left with 2 to the 5th from those two terms in the denominator times n plus 1. This is a rational expression with n, same highest power, so we look at the ratio of coefficients. That's going to be 2 over 2 to the 5th, which is 1 over 2 to the 4th, so this is 1 over 16. Careful, that's not the radius of convergence. That's the limit as n goes to infinity of the coefficient ratio. So that's this limit. Since this limit exists, it equals 1 over 16, that tells us the radius is 1 divided by that number, so it's 16. Let's finish this example by using it. So at the top here, I've put the Taylor series that we've worked out for the function f of x equals 1 over the square root of x, centered at x equals 16. We are going to use this series now to approximate 1 over the square root of 17, and we want to do that in such a way that tells us that our first 3 decimal places are correct. What we can do now is say that 1 over the square root of 17 is like f of 17. So we'll let x equal 17 in the line above. Fortunately, what that means for this final term is that it's always 1. So this last part here equals 1 when x equals 17. So that's good news. Let me take the coefficient here, not including the leading sign changing expression negative 1 to the n, and I'm going to call that a sub n. So let a sub n be this part without the switching sign at the front. So that's going to be this odd number product down to 3 times 1 divided by 2 to the 5n plus 2 n factorial, and then times 17 minus 16 to the n, but that number is always 1, so I'm not going to write it. We just worked out that the radius of convergence for this power series is 16. So since 17 is between 0 and 32, that means that I can say that 1 over the square root of 17 can be written as a convergent sum of numbers for this series. So plug in 17 and we would get equality on both sides. So let me now start to write out the expansion in terms of this new expression a sub n that I've introduced. The first term is negative 1 to the 0 times a sub 0. So that's a sub 0 minus a1 plus a2 minus a3 plus a4, etc. If I could do this forever, we would have equality, but that's not what we want to do. Instead, we want to use these terms to estimate 1 over the square root of 17. In order to guarantee that our first 3 decimals are going to be correct, we'll use the alternating series remainder theorem. This is going to have the alternating series remainder. What this said was that if you look at the true value of a convergent series of numbers of an alternating series, so say I look at the actual value of 1 over the square root of 17, If I measure the distance from that number to the partial sum going through, let's say, a sub k. So if I measure the distance between the true value and the estimation starting at n equals 0 and going through some top index k, -1 to the n a sub n, this distance, which you can think of as the size of the remainder, the size of the error, is no larger than the next term a sub n plus, or a sub k plus 1. So one way to figure out how many terms you need to add up in order to get the level of accuracy that you're looking for is to work with this expression over here and see what k has to be in order for that number to be sufficiently small. I'm going to take an alternative approach here. What I'm going to do is start writing down a sub 0, a sub 1, a sub 2. I want to see how small they get until I realize that I've written down enough terms in order to get the first 3 decimal places correct. Okay, so let's do that. I'm going to say, what is a sub 0? That's when n equals 0. So this part is actually just going to be 1. And then we have 2 squared times 0 factorial is 2 squared times 1. So it's 1 over 2, 2 to the 2. So 1 over 4. Might have said that incorrectly, but overall the answer is 0.25. So that's the first term in the series calculation for 1 over the square root of 17. I just went and got my notes for A1 and A2 because I worked them out earlier. Assuming that I did this correctly earlier, a sub 1, when you plug 1 in for the index, you get 2 times 1 is 1. So this is the odd product through the number 1, so just 1. Divided by 2 to the 7th times 1 factorial. So overall, that's 1 over 2 to the 7th. And that's approximately, actually, this might be exact. Well, 0.0078125. I think that's probably exact. It's pretty small, but we still have some non-trivial action happening in the first 3 decimals. So what about the next term, a sub 2? That is going to be 3 times 1. Yeah, I just blanked out for a second, but this is 3. Okay, 3 times 1 divided by 2 to the 12th times 2 factorial. So that's 3 over 2 to the 13. And that is approximately 0.0003, I believe, 66. Again, assuming I can read my own handwriting here. Notice we have these 3 leading zeros. So the next term is going to be even smaller. At this point, I think we've got enough. And in fact, if you do a sub 0 minus a sub 1 and compare that number to a sub 0 minus a1 plus a2, they have the same leading 3 decimal places. A sub 3 is going to be sufficiently small. So that means that if I add up, say, the first 3 terms, my first 3 decimals are correct. So the first 3 decimals for 1 over the square root of 17 are 2, 4, 2. Okay, so this was an example of using a power series in order to estimate a quantity. In this case, to estimate 1 over the square root of 17. In the next few videos, we will work through Taylor series computations for some famous functions. So we'll see natural log, e to the x, some trig functions, expressions like that. And you might find them actually a little nicer to work with than 1 over the square root of x like we did in this example.